Okay, so we are going to tackle test number 2 review. Remember, you have a digital copy of this available on Blackboard, and the answer key is also available, but I'm going to work through the problems. That way we have a video to work off of as well. Everything on this exam, or this practice test, is, excuse me, is from chapter 2, except for number 1. Number 1 is left over from chapter 1, because it's a good thing to be reminded of, and also it's a good reminder to know that as we move forward, while some of the stuff may not show up on the test from previous chapters, the final exam is comprehensive, and so you definitely don't want to just lose all of this information as we progress. So it says solve the following inequalities and graph the solutions on the number line. So remember, when we tackle an inequality, it's no different than when we tackle an equation. It's just instead of getting one solution, we get a whole interval of solutions. And so when I look at this inequality, first thing I'm going to do is I'm going to distribute to try and simplify, because I want to get all my x's on one side. I want to get all of my constants on the other. So 3 times 4 is 12. 3 times a negative 5x will be a minus 15x. And then we have 30 minus 9x over here. So I'm going to do a bunch of stuff all in this one go. You guys can keep up with that. I'm going to move all of my variables to the left and all of my constants to the right. So to do that, I'm going to add 9x to both sides, and I'm going to subtract the 12 to move it over. Now, you may choose to move in the other direction, and that's totally fine. It's up to you. You do you. You're going to get the same answer as long as you pay attention to what you're doing. So when I subtract the 12, that moves it over. I have negative 15x plus 9x, which will give me a minus 6x, is greater than, I have 30, take away 12, which is 18. One of the reasons I purposely decided to move things to the left in terms of my x's is that I knew it would result in a negative, and I wanted to make sure that we pay attention, because on our next step, we have to divide by a negative 6. And this is the one time where a special rule pops up with our inequality, where if we divide by a negative, we have to flip our sign. And so the negative 6 is over here, cancel out, and I'm left with x. Instead of greater than, I'm going to have less than. 18 divided by negative 6 is a negative 3. And so then we get to label our number line and move from there. So I'm going to do, let's see, 4, 3, 2, 1, 0, 1, 2. You may have different numbers on yours, that's totally fine. What is important is that if x is less than negative 3, that's everything to the left of the negative 3. And since it's strictly less than, I'm going to use the parenthesis, or you're allowed to use the open circle. You can do either one, you do not have to do both. Then I'm going to make an arrow headed to the left, and I'm going to shade in everything in here. So a big thing is that you want to make sure that you have this arrow, because this arrow indicates that it goes on forever in that direction. Make sure you shade in, and then either an open circle or a parenthesis, whichever one you want. I'm showing you both just so that you know both are acceptable. And then that's it. We're done with that one. Now, the next one is an OR problem, and it has it split up into 2 separate inequalities. That's totally fine. We're going to treat it as 2 separate inequalities the entire way through it, and then we'll see if it has an effect on the graph or not. So if I have 3x minus 1 is less than negative 5, then to isolate my variable, I'm going to add 1. So I have 3x is less than negative 4. Divide by 3. X is less than negative 4/3. Okay, not super interesting. That's okay. Same process over here, but what's changed is my sign has changed its direction, and it's gone from a negative 5 to a positive 5. So I will get out a different answer, even though my steps are going to be exactly the same steps. I'm adding 1 to both sides, which will give me 3x is greater than 6. I'm going to divide by 3, and I find that x is greater than 2. So remember, this is an OR problem, OR. So when you were an OR problem, remember that was our union problem. That's where we take all of this stuff and we add to it all of this stuff. Intersection is our AND one. That's where we have to find what they have in common. This one, we're not looking for what they have in common. We're just saying we're going to take all this stuff and we're going to add to it all this stuff. So -4/3 is like -1 1/3. So I need to keep that in mind as I label my line. And then I have to go at least to 2. So let's do 3, 2, 1, 0, 1, 2, 3. That'll work. I usually go about 1 or 2 units past my limit points, just so that I have a good idea of what's happening. Now, at -4/3, you might want to label that -4/3. You're either going to choose, again, these are strictly less than or strictly greater than, so you're going to choose to use parentheses or the open circle. If x is less than -4/3, then we're headed to the left once again. And again, I'm going to use arrows and I'm going to shade it in. Open circle or parenthesis, whichever you prefer. The other part of our inequality says that x is greater than 2, though. So at 2, again, we're going to use a parenthesis or an open circle. And then we have an arrow shooting off to the right this time. And so we actually have 2 different sectors that are getting included in this inequality, because x can either live here or x can live here. And so that's how we do those. All right, 2, given the functions f of x equals 9x plus 4 and g of x equals x minus 1, find the following and give its domain. So we have 2 different parts to all of these that we're doing down here, and we're doing all 4 of the algebras of functions. So we're going to add, subtract, multiply, and divide. And if you remember, the only time we had issues with our functions is if we had radicals or if we have fractions where our x is in the denominator. If I look at these 2 starting functions, both of these are lines. So that means my starting domains are -infinity to +infinity. And when I add, subtract, and multiply, that does not change my domain. So that makes our job really easy when it comes to finding the domains for these. All right, so let's look at this. If I take f of x plus g of x, I'm literally taking f of x and I'm adding to that g of x. This is simply combining like terms. That's all we're doing. So f of x was 9x plus 4, g of x was x minus 1. So I combine my x's to give me 10x, and I take 4 minus 1, which will give me a +3. That is my solution, 10x plus 3. Do not be tempted to solve. Do not be tempted to set it equal to 0 and find out what x is. None of that stuff. This is all we're doing. Then the domain of this, as I mentioned, the domain of f was -infinity to +infinity. So the domain of g was also -infinity to +infinity. So when I add those together, nothing happens. There's still no trouble spots. So hopefully this is going to give you some easy points. All right, with subtraction, we do have to be a little bit careful, because when I subtract my g of x function, that negative is applied to everything in my g of x function. It's not just to the first term of my g of x function. And so when I write it out this time, I'm going to make sure and put parentheses around my g of x function. That way I remember to distribute the negative inside, because that negative is going to go to the x and the negative goes to the -1. That'll give me a 9x plus 4. Negative times a positive will give me a -x. Negative times a negative will give me a +1. Now I'm ready to do my combining the like terms. 9x minus 1x will give me 8x. 4 plus 1 will give me 5. And again, because I had -infinity to +infinity for both of my original functions, when I subtract them, I don't get any new trouble spots. Nothing bad happens. So that'll be -infinity to +infinity. When I multiply, then I'm taking f of x times g of x. Both of these are binomials, and when we multiply a binomial times a binomial, then what we're doing is FOIL, first, outer, inner, last. So I'm going to take first, which is 9x times x, which is 9x squared. Then I'm going to take outer, 9x times a negative 1, negative 9x. I'll do my inner, which is 4 times x, which will give me a positive 4x. And last, which is 4 times negative 1, which will be negative 4. Now I'm ready to combine my middle two terms here so that I end up with 9x squared minus 5x minus 4. And even when we multiply, that doesn't change our domain at all, because if you notice all of our results, we've had a line, and now we have a quadratic. The domain for all of these different types of functions is always a negative infinity to positive infinity. So we haven't had any issues with that. It's always when we go to divide, even if we start off with really nice functions like this, that we're going to have at least one trouble spot that happens. It just does. Let me shift this down a little bit. There we go. So if I'm taking f divided by g of x, that's where I take my f of x function and I stick it on top of my g of x function. So in this case, my f of x function was 9x plus 4. My g of x is x minus 1. So that's my answer. There's nothing else I can do. I'm not going to try and do any other arithmetic with it, so that is my solution. But I do need to figure out where my domain is going to break down. And it breaks down wherever this equals 0, so we don't want it to equal 0. So what I'm going to do is I'm going to figure out, well, what values of x take my denominator to 0? And I do that by setting my denominator equal to 0 and solving. So when x is 1, my denominator goes to 0 and it breaks my function. So I cannot include 1 in my solution set or in my domain. And so what I'm going to do is I start at negative infinity and I go until I hit my trouble spot, which is 1. Then I'm going to union that with 1 and go to my trouble spot, or excuse me, go to infinity. I don't want to include my trouble spot of 1, so I use parentheses and I put a union there. So if you have one trouble spot, you're going to have one union in your domain. If you have 2 trouble spots, you're going to have 2 unions. If you had 3 trouble spots, you'd have 3 unions, and so on and so forth. Because that union is always going to be wherever the trouble spot resides. All right, let's flip over to number 3. Is all about determining if a given function is even, odd, or neither. And I showed you the hard way, and then I showed you the easy way. So we're going to do all of these the easy way, because I'm all about that. So the easy way is where we look at the powers of our exponents, and that's going to tell us if we are even, odd, or neither. This first one, we have f of x is x to the third minus 6x. Now this x doesn't have an exponent written on it, but we understand that there's a 1 there. So our exponents in this case are 3 and 1. So all exponents are odd. That means we have an odd function. Now, on the exam, do you have to put all exponents are odd? No, you literally just have to put the odd on there. I put extra notes in the key in this presentation just so that you can go back and look at it and understand how we got this. For g of x, we have x to the fourth minus 2x squared. In this case, all of our exponents are even. 4 and 2 are even numbers. And if all of our exponents are even, then we have an even function. And then our last example, our h of x, is x squared plus 2x plus 1. So this x squared has a 2, that's even. The 2x has a power of 1, that's odd. And then the 1 is a constant. And remember, whenever we have a constant, that's like saying x to the 0th power. And in terms of even, odd, and neither, we always classify 0, x to the 0th power, as an even. So we have 2 evens and 1 odd. Since we have both even and odd exponents, we have a neither situation. You either have to be all odd to be odd, all even to be even, and if you have some combination of even and odd, then you are a neither. And that x to the 0th power is classified as even, so be careful about that. If you have like an x squared plus a constant and there's no middle term, then this would be classified as an even function. All right, number 4. Ooh, sorry, that got crooked. Number 4 is given f of x equals x squared minus 1 and g of x equals 4 minus x, find f of g of x, g of f of x, and f of g of 2. So this is our composition of functions. This is where we take one function and we shove it into another function. And so I like to write them as f of g of x this way because this looks like our function notation. And this tells me that I'm going to take the g of x function and shove it inside my f of x function anywhere that there is an x. And so I'm going to do that first. My f of x function says x squared. Well, instead of x, I'm going to put g of x. So that'll be 4 minus x squared minus 1. This is my f of x function with my g of x function shoved inside. Now, we are not going to do magic math. We're not going to say that this is 16 plus x squared. That's magic math. In order to do this power of 2, we have to do FOIL. 4 minus x, 4 minus x, and then we still have the minus 1. So don't try and cheat it and go too fast, and then you lose it. So, FOIL, first, outer, inner, last. I'm just going to write all that on there so I don't have to use that pen again for a little bit. So for my first, it's 4 times 4, which is 16. For my outer, I have a 4 times a negative x, which is a negative 4x. My inner, I also get a negative 4x. And then my last is a negative times a negative, which means I get a positive x squared. And then I still have this minus 1 out here. Watch out for that because it's easy to let that go and forget about it, and then your answer is going to be wrong in the end, and that's a big bummer. Now, I'm going to reorder this so that my x squared term comes first, then my x term, then my constant. So x squared, I only had the 1, then I have a negative 4x and a negative 4x, which gives me a negative 8x, and then I have 16 minus 1, which will give me a plus 15. And I provide these lines for you to put the answers on, so I appreciate if you actually do put your answers over there. It makes grading so much easier. All right, now we're going to do g of f of x, because we've seen in the past that g of f of x is not equal f of g of x. These are different. And so in this case, I'm going to take my f of x function and shove it inside my g of x function anywhere that there's an x. So I'm going to have 4 minus my x, but that's my f of x. And because I am being very careful, I know that that negative applies to everything in my f of x function, so I'm going to put my f of x function inside parentheses, so I don't forget to distribute that negative to everything inside. So that goes to the x squared, and it's going to go to the negative 1. So that'll be 4 minus x squared, and then a minus minus will make it a plus. Listing my x squared term first, and then 4 plus 1 is 5. These are very different answers between these two. Now, my last one, f of g of 2, can be done 2 different ways, and I will show you both. You do not have to do both on the exam. I'm just going to show you both. The first one relies on you having done part A correctly, which is a big, I would say concern. I don't know if that's the right word, but it's a risk. If you dropped a negative somewhere up here on part A, or you flipped a number, or you dropped that number 1, and you go back and you use this answer on part C, then you're going to get part C wrong as well. So this first way I'm going to show you is risky because you're banking that you got this first part right. But we're going to do that. Because f of g of 2 means we're taking our f of g function that we just created and we're plugging in a 2 everywhere that there's an x. So that would be 2 squared minus 8 times 2 plus 15. 2 squared is 4. Negative 8 times 2 is a negative 16 plus 15. This would be negative 16 plus 15, which will be a negative 1. So that gives us 3. Okay, so that way is the risky way. Do I always recommend the risky way? No, usually I recommend the not risky way. So the not risky way is where we remember that f of g of 2 means we can find g of 2 first, and then plug that value into our f of x function and find our f of g of 2. So first thing I'm going to do is find g of 2. The benefit of this method is I am not relying on any of my previous work. So if I did mess up part A, it's not going to affect me if I use this method. So what I'm going to do is I'm finding g of 2. So anywhere in my g of x function I have an x, I'm going to substitute in a 2. So that would be 4 minus 2, which is 2. Not too hard. Now, whatever solution you get here, you're going to plug into your f of x function. So in this case, we're finding f of 2. Will this answer always be the same as what we plugged in? No. It just happened to be that way for this one. So now I'm going to go to my f of x function, which was x squared minus 1, and I'm going to plug in a 2 everywhere that there's an x. So x squared would mean 2 squared minus 1. Well, 2 squared is 4. 4 minus 1 is 3. Notice we got the same answer. This is a great way for you to check your work. If you do it both ways, then you know for a fact that your first answer was correct if these match. If you do f of g of 2 this way and you get 3, but when you do it this way you got 5, then that tells you that there's something wrong with how you did your work up here on A. So you can check yourself with that. This red way is kind of the way that I usually recommend students approach it, simply because, again, you're not working off of information you had to obtain. But either way, because we did it right, it's 3. All right, let's do some graphs. Lots and lots and lots of graphs. So let's go through and we'll do the matching part probably last. We'll go and do the function part first, and then we'll do domain and range of all these, and then we will match, just simply because I know I have to move it to show you the equations versus the pictures. So this is where knowing your mother functions is going to be really, really important, because it speeds up the process of you determining which graph goes where and what is what. So if I'm looking at this function, or really we could look down here and make it even easier. Because a function is a function if it passes the vertical line test, right? So if I look at my pictures, if I draw a vertical line on here, is it going to hit my graph in more than one spot? If the answer is yes, then I'm not a function. But if I can draw vertical lines and it only hits my function in one spot, then I am a function. So yes, this is a function. Draw, 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 draw. I only hit my graph in one spot, so yes, it's a function. Lines are always functions, so that one's a function, and then we have another line down here as well. So that's a function. And then this is a big V, but again, even if I draw my vertical lines, it only hits in one spot, so yes. And then here, this is a curved one, but even then, if I draw my vertical lines. So all of these are functions. None of them messed up, none of them hit in more than one spot. Now, when I go to do the domains, I'm going to come, and I'll do the domain and the range of each graph as we move across. So, domain and range for this first one, this is like an upside down swoosh. Domain refers to my x values. And it says that I need to make my domain and range in interval notation. So interval notation is where we use parentheses or brackets based on what our situation tells us. So if I'm thinking about the domain, which is all of the x's that work for this function, the first thing I'm going to notice is that my function stops at 0. I have no negative x's in this function. So my lower limit is going to be 0, and it's included with this graph. There's no open circle here. It's a filled in circle at 0, so I'm going to include it. And then it shoots off in the positive direction for my x's. So that would be the domain, from 0 to infinity. My range, though, is a bit different. Range has to do with y's. So that's my verticals. So if I look up here in the positive sector of my y's, there's no graph. So I have 0 for my y, but then I have -1 that would go over, and -2 and -3, because it keeps going on with the swoosh. It'll keep going down and down and down. So my lower limit for my range is actually going to be -infinity. And then my upper limit will be 0 with a bracket, because again, I do hit 0, but I don't ever get any positive values for my domain, or excuse me, my range. And so we have to look at the graph, and we have to be able to deduce what it is telling us. For our B graph, we have this upside down parabola, and the domain on this, remember, that's our x values. So since these have arrows, it tells you it's going to go out and down for forever. So looking at the x's then, is there any x value that's going to be omitted or not included? And the answer is no. All of our x's will eventually, we could draw a line down and we would hit our graph. So our domain would be -infinity to +infinity. But our range, again, is a little bit different, because look at my y's. They shoot off downward for forever, so I'm going to have a lower limit of -infinity, and then how high up do I get on my y's? I get all the way up to here at this maximum point, which is at -3. So I go all the way to -3, and again, I include that in my bracket because it's on our graph. Lines, these are nice, these are easy. Lines go up or down for forever depending on which way you're reading it. It's going to have all of our x values included and all of our y values included as well. The only type of lines that don't, a vertical line, that's not going to include all my x's. It will include all my y's, but not all my x's. And it also is not a function if it's a vertical line. But if I have a horizontal line, that includes only one y value. And so you would put that just inside curly brackets or list it inside brackets. Let me do an example. Let's say I had a horizontal line here at y equals 1. That would be the equation for it, is y equals 1. This is a function because it passes the vertical line test. The domain would be everything. But your range in this case would only be that one point, which is 1. So you would write it like this, or you could write it in curly brackets. You would not use parentheses because we do include that 1 in our solution set or in the interval. But either of these would be completely fine. Sorry, that was a little tangent. Okay, this V, is there any x that we are not going to hit? Nope. We will hit them all, so that'll be -infinity to +infinity. Our range, though, is kind of the opposite of like what happened up here. Our range starts at 0, and then it keeps getting more and more positive. So we will go from 0 to +infinity for that one. E, we have another line. Lines are nice. We go from -infinity to +infinity. All is glorious. And the last one, we have this curvy one. This is also -infinity to +infinity for both the domain and the range. Nothing is going to be excluded. Now the only thing we have left to do is actually match. And so if you have something of your mother functions memorized, it makes this job a lot easier, because I know when I have something that looks like a swoosh, this has something to do with our square root. And so I'm going to come down to the bottom then, and I'm going to look at my different equations, and I'm going to look for the square root, because none of the other ones look like this. And we only have one that's a square root, and it has a negative. And we learned in 1.5 that when the negative's out here, that's when we reflect over the x-axis. It affects our y's. This is a reflection situation going on. So A is 4. B, sorry, you couldn't see the 4. B, even though it's a little bit wonky, is a parabola. Okay, it's a parabola, and parabolas are x squareds. And we only have one x squared that happens here. And notice it's got a negative out front, which tells us it flips over the x-axis, and it has a vertical shift, and it's down 3 units. That's exactly what we had happen here. So this page is really good at helping you to familiarize yourself with your mother functions, but it also helps you to do a lot with the 1.5 translation of functions. So B is 2. I'm going to skip C for a minute because it's a line and I know I have another line, so I'm going to leave that for a minute and I'm going to come to the V shape. The V shape is the absolute value, and we only have one absolute value, and it is the mother function itself. So D is 5. Again, I'm skipping the line and I'm coming over here. So we have 2 lines left and then this one. This is your cube. This will be 3. This is f of x equals x to the third. So again, this was another mother function. There was no translations or movements on it. So now I'm down to 2 different lines. I have this line, which goes through the origin, and I have this line that goes through 1, 2. Goes through y equals 2. So if I look at my different equations, I've used this one, this one, this one, this one. So I'm down to f of x equals x and f of x equals x plus 2. Hopefully, because this is a line, this looks like y equals mx plus b. That b tells you where you cross your y-axis. This one crosses at 2, so the 6 would have to go with the c. E would have to be 1, because we have the point 1, 1, 2, 2, 3, 3, 4, 4, so on and so forth, because our y's equal our x's. All right, flip over to the last page. This is the big one, because this is our translation of functions where we will actually be doing the graphing of it. So again, if you don't know your mother functions, you're not going to know what the general shape is, and you need to know your general shape. So learn the mother functions. And we also need to know what these different numbers tell us. Now, the numbers and the negatives and where they live at. If you blank on the test about what this negative does, or what this plus 4 does, or what this plus 1 does, you can always come over here to the side and you can make yourself a table. And you can plug in random x values, plug them into the function and get their outputs. And that will give you some general ideas of what's happening with this graph. It takes quite a bit longer, but it is a good way if you blank on what the mother function of this might do. Now, hopefully, though, and one of the reasons why I give you the page before, hopefully, because this is an absolute value, if you have an absolute value one on the one before, you can use this as a general idea of what's happening. So I know I should have a v, and originally the mother function looks just like this. It's a v straight up, straight down, starting at 0, 0. So that's what my overall picture should look like. I should have a v. Now, I'm going to talk about the different movements or translations that are happening, though, because that's what's going on here. This negative out front, because it's outside of the absolute value, tells me I'm flipping over the x-axis. Flip over x-axis. So if I'm thinking about the v then, since it started all up here, if I'm flipping over the x-axis, my v is going to be shaped downward now. So I'm just going to kind of make a note. That's what the negative tells me. This plus 4 inside of my absolute value, since it happens inside the function itself, is a horizontal shift. And horizontal shifts affect your x's, and that means they go in the opposite direction of what you think. So they're actually going to head to the left 4 units. And then the last number, that plus 1 that's just hanging out there on the end, since it happens outside the function itself, is a vertical shift of up 1. Now, we kind of have to remember our ordering here of what we're allowed to do when. And so if you don't know your order, that's going to make it difficult. So the first thing we're going to want to do is we want to do our horizontal shifts. So I want to take everything to the left 4 units. And so remember, I'm thinking about the mother function. So I start at 0, 0, but instead I'm going to go to the left 4 units. 1, 2, 3, 4. Now originally, I would do my v from that point, but I have to flip over the x, which means my graph would go downward. Okay, but I still have this plus 1, which means I go up 1 unit. So that vertex actually is going to start here. Instead of 0, 0, I'm starting all the way over here because of all these different translations. And then instead of headed upward like a regular absolute value graph, I'm going to head downward. Now, I don't expect you to bring a ruler to class to do this, so do your best. But I do expect for this to run through like these intersections, because that's what the absolute value says, and I expect it to be sharp point. If it's a quadratic, then you do a rounded U shape, but there needs to be a distinction between the absolute value, which is a V shape, and the quadratic, which is a U shape. So make sure you spend a little bit of time with that. You also want to make sure that you put arrows on the end of your graph. If you don't put arrows on there, then you're telling me that the graph ends wherever your line ends. So those arrows indicate that it goes on forever and is very important. Okay, now we're going to answer a bunch of questions about our graph. And hopefully, because we just did the graph, it's going to all just fall out. So the first thing is, was there a vertical shift? Yes, there was. And then it says, if so, if there is that translation, state the value and the direction. So there's two different ways we could do this, and I'm going to show you the way that I prefer it. You can do an arrow indicating which direction we went. We went up 1, or you can put +1. I prefer the arrow method because when it comes to horizontal shifts, they go the opposite direction. So, yes, there was a horizontal shift. In this case, we went to the left 4 units. But if we're headed to the left 4 units, then you could make an argument that this is a +4 or a -4, depending on how you look at it, which is why I don't really love the plus and minus situation. But in this case, I would put it heads in the direction of the -4. So be careful about that. There was a reflection. We reflected over the x-axis. So you can say about or over whatever axis it is. Remember, if it's going to be reflected over the y-axis, then that negative is going to fall inside of the function itself. Was there a vertical stretch or shrink? No, there was not, because there's no number out here in front of our x or out inside of our function itself. And so there's no vertical or horizontal stretch or shrink. So make sure you circle these yeses and nos and don't just go too fast, because if you know that there's not a vertical stretch and a horizontal stretch or shrink for this, but you don't circle those, you miss out on those points. And those are easy points. So don't rush. For the next one, we're going to talk about increasing, decreasing, and constant. And on the test, it actually says if it doesn't happen on the graph, you're going to write nowhere on the line. So it does state that in the actual test. It doesn't state that here on the practice test. So just be aware of that you're not going to leave any of these blank. You're going to give me something, okay? You're either going to give me an interval or you're going to give me the word nowhere. And if you leave it blank, you miss the points. Again, easy points. So remember, increasing is where we are going up, decreasing we are going down, constant is where it would be a flat line. So in this case, we are increasing until we hit -4. These intervals deal with our x values, okay? X values. Or domain. You could think about them like that too. They're kind of like the domain. So we are increasing from when x is -infinity until x is -4. On these increasing, decreasing, and constants, we will always use parentheses because at -4 is our turning point. And so we are both increasing and decreasing at the same time at that point, so we don't include that point in either of our actual intervals. We just get really, 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 really close. Okay, so I'm increasing till I hit x is -4, and then after that, I am decreasing for the rest of time. That's a really wonky infinity. And then am I constant anywhere on this graph? There's no flat spots, horizontal spots, so I would write nowhere. And then the very last bit says, state whether the graph has a relative minimum, that's a lowest point indicated on the graph, or does it have a relative maximum? Since my graph is faced downward, I have a maximum point. There is a value at which we are going to get the highest y value we possibly can. This is a maximum. If I had had an originally oriented graph like this, then I would have a minimum point. So I have a maximum, so I'm going to say yes on the maximum, but I'm not going to forget to circle the no on the minimum because I don't want to miss out on those points. Now there's nothing we have to put over here. We can leave those blank. Yes, we do have a maximum point. It happens at x equals -4, because that's where it's happening at, with a value of what? what is our y value when we're at negative 4? Well, we're at positive 1. So it has a value of 1. And that is how you will fill out that last section.